Everybody okay on the way we measure these voltages, the names of the voltages, right? And then the voltages across the transistor. Tells us where the black lead at, right? So the right letter tells us where we put the black lead on our meter when we measure these. Transistor is a switch. By the way, when we get into sensors, we have what we call DC sensors, and the term that we use, and this came from digital, we have what we call syncing sensors and sourcing sensors. So a syncing sensor provides a common or minus. So a syncing sensor provides the minus, provides the plus. On DC, and then a sourcing sensor provides the plus. But normally they refer to them as NPN and PNP. So this is the PNP. So this is PNP. So notice the emitter's pointing back toward the positive power source. We bring in something that's smaller than that, and then here's my load right here. So my load is actually connected to the collector. And that's what we're trying to do here, is we're trying to connect it to the collector. So a PNP sensor is a sourcing sensor. Now notice the NPN sensor, this is common by the way. The load is up here on the collector. So the collector is connected to the plus. This is an NPN. And so what happens, the PNP, an NPN sensor provides the common, a PNP provides the source. Does that make sense? And so this is something you have to, a PNP is a PNP sensor is a sourcing sensor. An NPN sensor is a syncing sensor. Now, why do we need to know that? Because of programmable logic controllers. So when we come over on a programmable logic controller, this would actually be the sensor. And then the sensor is going to input into the PLC. So that means if it's a sourcing sensor, if the sensor's sourcing, then the PLC input has got to be what? Because if this is plus, and this is where my sensors will be at. Now this is my PLC. So we got to have current flow through it, and current flows between that. So a sourcing sensor would hook into a syncing input. That makes sense? Yes or no? No, the PLC is a computer. It's not an output. So basically, a PLC runs up like this. We have a sensor or some type of input that's over here. Then we run this into an input port on the PLC. And it's got to be a complete circuit, right? You understand that? Yes or no? Then we process it with a program, and then we run it into outputs. So let me so basically on a PLC we have so on a PLC we literally have two different circuits. We have an input circuit and we have an output circuit. And we can go back here and look at it. So So this is my input side, and it's got two lines, and here's my output side over here. So the inputs and outputs are not connected together. And in between here, we have a program. So over here, we're going to connect our inputs right here. Then this is going to come into the input of the PLC. And so all my input devices are going to be connected over here. So these are inputs on my PLC. I'm just going to put in. And these right here would be like a sensor or a switch or something. It don't make any difference. So this could actually be like a push button. And then the push button would connect up to a PLC. Well, we got to have current flow, right? You understand that? So if this is positive, then what does this over here have to be? Negative. So we use the term common all the time, but technically a common is just one thing that all the different things connect to. So over here, my sensor is using a plus common. So my PLC has to be using a what common? A negative. So that means if I use a sourcing sensor, then my input has got to be what? Now my input's got to be syncing. And if I came over here and used a syncing sensor and a syncing input, you're not going to hurt anything. It's just the input wouldn't work, right? You understand that? We got to do the same thing over here. So this is my output. And then this right here would be the load, whatever the PLC runs. So if this is plus over here, then this has got to be what? Minus. And this is, over here in the US, this is the standard way we run our DC PLCs. We have syncing inputs and we have sourcing output. So that means over here I'd have to buy PNP sensors, right? You understand? Because sourcing inputs require, a sourcing sensor hooks up to a syncing input. Everybody understand that? That makes sense? So this is important to know because if you, in every manufacturer I know of, I'm not going to say that, but most manufacturers make the same sensor as either a PNP or an NPN. And if you buy the wrong one, it's not going to work. It's not going to work. And odds are you tear it out of the package, you hook it up, and you find out it's not going to work. They're not going to take it back, right? You understand? Because it's been taken out. So. And we talked about a constant current source. So how do we set up a constant current source using bipolar transistors? Well, first of all, we need to know what the load needs, right? Well, not really. I'm going to come over here, and I'm going to put a emitter resistor right here. And on ours, we put plus 5 volts, and originally we connected it straight up to plus 12. And we said this was a what? This was a 220 ohm resistor, right? We're going to call that RB. So what would be the voltage drop? What would be VRB? Approximately what? Different circuit. Different circuit. Yeah, we're going back because we wasn't able to record this. So VRB would be a VRB if we call this transistor, if we call that resistor RB, what would the voltage drop would be across the thing? Yeah, it'd be 4.3 volts. Then IRB, it's going to be equal to 4.3 divided by 220. We came up with what? Milli. So IC would equal to approximately what? It's a series circuit. What's that? A voltage collector to emitter would be equal to what? It's a series circuit. This guy right here is dropping 4.3 volts. What's my voltage collector to emitter? Kirchhoff's Kirchhoff's law says the sums of the voltage drops have to equal to the applied voltage. I've got one guy, 4.3, so what would VCE be? What's that? Then we came over here and we put a LED right here where it says about 2 volts. We don't know what it is, but it was, yeah. So now this guy's dropping 2 volts, this guy's dropping 3, so VCE, so the resistance of the transistor automatically changed to keep this current at what? Keep the current at what? 19.5. So I came over here and put another LED over here. What was the current? 19.5, right? You understand? Until we ran out of the watt. Instead of ran out of 12 volts. So this is a constant current source. Is this going to change with temperature? No, because this guy right here is set at 4.3 volts. Right? You understand? This will change its temperature. If I came over and put a resistor right there and come over here and put my emitter directly to common, this guy right here will change with temperature. If I came up here and if I originally set this as plus 12 and I sized the resistor to give me 6 volts, if the temperature went up, the voltage would go down. If the temperature goes down, the voltage across the transistor goes up. Because it won't change. Because if this guy here don't change, and this guy here don't change, which means that it changes a little, but not enough to hurt, right? This is a constant current source. So I can keep adding LEDs, and each one of them work fine until we run out of voltage, right? So this is voltage divider bias right here. And why do we call it voltage divider bias? Because the base voltage is set with a voltage divider. And once we set the base voltage, and we set it at what? So let's rework this. So this was what? This was 100K. This right here was what? 10K ohms. This right here was 10K ohms, RC, and then this right here was 1K ohms. So where do we start this at? We calculate, first thing we're going to calculate is VB. But VB is technically the voltage drop across R2, right? You understand that? So VB, and we use the voltage divider formula, is going to be equal to, we want the voltage drop across the 10K, across RT, and then we're going to multiply that times, we were using what? 12 volts up there? And that gave us what? About 1.1 volt, right? Wound into 1 decimal point's fine, because all these are approximations anyway. So what would VE be equal to? It's going to be equal to 1.1 minus 0.7. So VE would be equal to what? What's that? It's actually going to go up, right? Can't be 490 and then we raise this voltage and we come up. So what would, excuse me. 400 milli. I didn't. I drew it wrong, right? So VE is IE is going to be equal to what? 1.1 divided by 1K. I'm sorry, guys. I don't want to confuse you. We need to calculate VE first. That's going to be equal to 1.1 minus 0.7, right? And we came up what, 400? Then IE equals to approximately IC, which is going to be equal to 400 milli divided by 1K. Are we okay? Lost anybody? What laws are we using? And Ohm's law, yeah. Then I can calculate VRC. What's VRC going to be equal to? 10K times 400 micro. What's that going to give me? We're calculating the voltage drop across RC. So as soon as we calculated this current, so we know we have 400 millivolts sitting right there, which gives me the voltage drop across RE. So then we calculated IE, which we're going to say is going to be equal to IC, right? They're not equal, but they're so close. Why? We can use them as the same. No, because we don't know this. See, this is the equivalent circuit over here. So here's RC, here's RT, we'll call that the resistance of the transistor, and here's RE. Why don't the voltage divider, I know this right here is what? I know this is 10K, I know this is 1K. Why does not the voltage divider formula work right here? We don't know RT. So the voltage divider formula is I can calculate the voltage, VRX would be equal to what? RX over what? RT. So I cannot use the voltage divider because I don't know the resistance of the transistor, right? Y'all understand that? That's whatever in a series circuit, that is whatever resistor in a series circuit you want to find the voltage across. And unfortunately, undoubtedly, they did not teach you the voltage divider formula in DC for series circuit. It only works with series circuit. So I could come up with any series circuit we'll come up with an easy one. Now let's say I come over here and I put this across a 15 volt source. And let's say this is a 1K, this is a 2K, and this is a 3K. I want the voltage drop across the 2K. So I'm going to say 2K, if we call this R1, R2, R3, then the voltage drop across the 2K, we'd say VR2 would be equal to 2K divided by 6K times 15. These cancel. So I know R2 is going to drop 1/3 of the voltage. I know it's going to drop 5 volts already. And this is what's nice about the voltage divider formula. A lot of times you can figure out the voltage without even plugging it into a calculator. I did that in my head. Why? using the voltage divider formula. So in a series circuit, because the voltage drop is proportional to the resistor, it's, what's the formula? VRX, which means any resistor in a series circuit would be equal to what? RX, Rich, over what? RT times VS. So I could come over and say, okay, what if this goes to 12 volts? Well, it's still going to drop 1/3 of the voltage. So now it's 4 volts. And that's what's nice. Now you don't have to recalculate anything with the voltage divider formula. I can throw any voltage on this circuit I want to, and R2 would always drop 1/3 of the voltage, no matter what's out there. Now, what would you have done in DC if I'd have changed the voltage? You'd have recalculated current, you'd come and you'd multiply them out. So all we're using here, guys, to calculate this side over here, we can use the voltage divider formula. Why can't I use the voltage divider formula to calculate this side over here? Well, they are in series, but the problem is, so here's the equivalent circuit on this side. So this equivalent circuit is easy to calculate because we know this R1 is equal to what? Well, we know it was equal to 100K. We know that R2 was equal to 10K. We know this guy right here was equal to 10K. I have no idea what the resistance of the transistor is. My mouse hit the floor, so and I lost everything. Oh, I know what's going on. So I know I have what? I know I have 400 millivolts drop right there, but I can't use the voltage divider formula. Why? Because of the transistor. So over here, I'm okay calculating this side. So this is 100K, 100K, Rich. This is 10K. And this is plus 12. This is the equivalent circuit on this side. So here's RC. Here's RE. I know RC is equal to 10K. I know REZ is equal to 1K. And then R, the transistor, I have no idea what it is. So I can't calculate RT, right? And then plus, as soon as I calculate it, we're going to put a signal in on this thing in a minute, and it's going to change, right? But I do know this guy right here is dropping what? 400 millivolts. I do know the size. Well, if I know the size, then I can calculate that current, and that's going to be equal to IE. So IE is going to be equal to what? 400 milli divided by 1K. I know the size of that resistor, and we came up and got 400 microamps. And I know that IE and IC are approximately what? Approximately, they're not the same, but they're so close, and we've got all these tolerances that we're dealing with, right? So is this exactly 7/10 of a volt? No. Is that resistor exactly 100K? No. Is that exactly 10K? So our math is perfect, but in transistors, we're going to use a lot of approximations. So now I can calculate VRC. So VRC is going to be equal to what? 10K times 400 micro, because it's a series circuit. And once I calculated this current, I know that current, right? You understand? So what's VRC? Good. Okay, so what's voltage collector to emitter? Voltage collector to emitter. It tells you the formula. It says I take whatever's on VC, which is what? Well, yes or no. Whatever's on the collector. Huh? So I know this guy's dropping 4 volts. I know this guy right here is dropping 400 milli. What's being dropped across that resistor right there? Kirchhoff's voltage law says the sums of the voltage in a series circuit have to equal to applied voltage. So I would say VCE would be equal to VRC, right? I'm sorry. I'll get the formula right in a minute, guys. It's going to be equal to VCC minus what? VRC minus VRE. So what's my voltage collector to emitter? 7.6. Good. By tendency, people want to say that. That's just a tendency because you just calculated that, right? And they forget that that's a voltage drop. If this thing don't come out of this, I don't know. So here's the circuit. Here's my 2 and 3904. Here's my plus 5 volts. I've got these guys connected together. Y'all see that? Y'all more than welcome to come up. Here's the 100K. I have these connected together on my base. Here's the 10K. So here's my base circuit. Here's my collector emitter circuit. Here's the 10K. This is the collector. The emitters on the left. Here's my 1K. This is my emitter resistor. So here's RC. Here's RB. Here's R1 and here's R2. So if I measure on the base, we should have about 1.1 volt, right? That's what we calculated. Here's the base. What's that measured? Oh, y'all can't see. Sorry. We're expecting 1.1. Oh, my turn. Can you see it? We got 1.05. Not too bad, right? If I look at the emitter, there's the emitter. We should expect around 400 millivolts. Can't really beat that, can you? Pretty good, right? That's 4. Oh, y'all can't see that. Now 400 millivolts. Okay. Here's my voltage on my collector. We're expecting 7 point. I mean, on my collector, we're expecting what? 7.1. 7.8. Not too bad, right? So 400 millivolts right here, 7. So that's my collector. I wish I had my soldering iron hooked up. I could heat this thing up, and this guy would sit here stable because of the divider bias, right? You understand? Okay, well, okay, so far. Pretty cool, right? So neat when the math and the circuit works out to be pretty close to the same. And why are they not exactly the same? Yeah, none of them's good. It worked out really, really well. So this guy right here is not dropping exactly. Here's not bad. That's on the emitter across. Okay, everybody okay so far? Okay, everybody follow so far? Lost anybody? Okay, 100K. That's rich. Now this guy would be nice and cute, right? But we need to be able to do something with this. So R1's equal to 100K ohms. R2 is equal to 10K ohms. RC was equal to 10K ohms. And R1 was equal to 1K ohm. I mean, RE was 1K. We calculated this. We calculated dB to be 1.1 volt. We measured 1.05. We calculated DE to be equal to 400 millivolts. We measured 400 millivolts. We calculated VRC. We calculated it to be at 4 volts. We didn't measure that. We calculated voltage collector to emitter. We didn't measure it, but we've got enough to measure it, right? So we know we have 7 volts. What we have up here, 7 point what volt? So we calculated this guy right here to drop 4 volts. We calculated we had plus 12 right there. We calculated this guy here to drop 400 millivolts. So what did we calculate VCE to be? Everybody okay? So all our calculations were actually based on 12 volts. So what do we actually have? 1.8. So we use 12, right? I understand that. Here's our voltage on our collector. We thought it was going to be 7.6, and it's actually what? 7.8. Here's our voltage on the base. I'm sorry, on the emitter. I don't know why it's jumping around the state of the rock. We calculated to be 4. Let's measure about 4.04. So what's our measured? What's our measured voltage collector? That was our calculated. Our measured 7.8 on one side, right? Here's the emitter. 4.1 on 7.8 on this side, 0.4 on this side. So what we end up with our voltage collector's emitter. What was our measured? It's actually about 0.4, guys. My meter's not around here. 7.8 on the collector, 0.4 on the emitter. So what's our measured? 7.8 on the collector, 0.4 on the emitter. What's our voltage collector to emitter? 7.8 on the collector, 0.4 on the emitter. What's our voltage collector to emitter? Can't come up with more than you start off with. We calculated, this is what we calculated. I measured 7.8 here. I'm measuring 400 milli right there. What's the voltage between that? 7.6 minus 400 milli. That's the difference here, right? Y'all understand yet that or not? Got 400 millivolts right there. I have 7.8 volts right there. What's the difference between 4.8 and 400 milli? Not 4.8. Did I say 4.8? 7.8. That's what we measured. Yes. Measured on the emitter. Okay, so voltage collector to emitter measured is 7.2. Calculated what? 7.6. Measured what? Calculated 1.1 there. Calculated 7.6 voltage collector to emitter. Calculated 400 milli. Calculated 4 volts there. Looks real good, right? Everybody okay? All right. Now, what would happen if I brought in an AC signal on the base? So we're just going to bring in an AC signal. What would happen? Yeah, it's definitely not going. Brought in an AC signal directly on the base. Gonna drop a lot. Well, we might have to get I might have to get a pot because this guy here's got. We've only got 1.1 volts to work with. So, oscilloscope. I'm using the function generator that's on the. So anybody got any ideas what I need to do? So when you see this on the scope, what is it trying to? What's your scope trying to tell you? Too much data? No, it's not static, guys. So what's my scope trying to tell me? My scope's trying to tell me that I'm tracing way too slow. So I need to increase the speed on my scope. And pretty soon we see a sine wave, right? So anytime you see this on a oscilloscope, it means your scope is going way too slow, right? But you notice as I slow down, my sine waves appear to get closer together, but that's because we're sweeping real slow, and eventually it's just going to draw that solid line right there, which is pretty neat. But I was had a DC offset on it, so I needed to set this in the center. Rich. This is a sine wave. Let's see, what are we triggering on, guys? Turn on channel 2. That's why it's moving around. So anytime it's jumping around like that, you need to say what you're referencing your scope on. So it's nice and steady now, right? You'll see that? So what would be the frequency? Let's slow it down some. Anytime you see this, it means your scope is tracing too fast. So I'm going to slow it down some so we get a sine wave up there. Okay. And we're running about 1.2 kilohertz. We could, because my scope's telling me that right here. Are we okay? All right. Are we okay so far? Okay, so what I'm going to do is I'm going to bring my meter back up here. If I can get this right. So here's my circuit again. Oh, can't get it. Yeah, I'm going to measure the base voltage. So what's our base voltage to be? 1.1 volt, right? Okay, now I'm going to bring this AC signal and I'm going to hook it up to it. And what did it do? Pretty much will drop to zero, right? You understand that? Take the AC signal off, come back up, put the AC signal on there, drops down to pretty close to zero. Everybody see that? Now what happens is we're connecting a source to a source. And I would be in real problems if I was to put it up on my 12-volt supply. So an AC signal sees a DC source as a straight piece of wire. A DC source sees an AC source as a straight piece of wire. So basically what I just did is I just come over here. As soon as I get my... So what I did when I hooked that source up is that basically I came over here and did this right here. I connected that thing just like that. So this voltage dropped down to approximately what? 0 volts. So what I need to do is I need to stop this from happening. So what I'm going to do is I'm going to come over here and I'm going to put a device in here that allows AC to go through it and it blocks DC. Anybody know a device that does that? Starts with a C. Capacitors. So capacitors block DC and they allow AC to flow through them. Huh? And we'll take a break here in a minute, guys. As soon as we see what I'm doing. What did we get VCE calculated? 7.6 volts. Now we're going to use a polarized capacitor. So what we're going to have to do is we're going to have to point the plus toward the base because it's got the, and then I'll come over here and then I'm going to put a sine wave right here. And when we actually do this, we'll have to use a potentiometer because The least amount of voltage I can get out of this thing is, I turn the amplitude all the way down. Oh, that's offset rich. Ooh, we might be able to do this. Times efficiency. Well, let's see if we get this to trigger. So this function generator works really well. So what I'm doing, guys, we'll take a break here in a second. I know I promised that. So what I'm doing is, if I can get this to trigger, if I want to trigger, is I'm bringing, we have it on 20 millivolts per division. I got 1, 2, 3, 4, 5, 6, about 7 divisions. So what am I trying to bring into this thing? 20 millivolts per division. It's not going to trigger, but we can trigger on the other side. Oop, there we go. No, dang it. So I have 20 millivolts per division. I got 1, 2, 3, 4, 5, 6 divisions. So what would be my voltage I'm measuring? $20 millivolts. That'd be 120 millivolts, right? Peak to peak. Okay, I'll take a 10-minute break. So yeah, this function generator right here is really good. We're gonna be able to do this.